Western Space and Marine Incorporated is based in Santa Barbara, California, and has been involved in producing specialized hardware for remote and hostile environments for the past 5 years. One of WSM's very special products is the arm, man's best combination of strength, dexterity, and sensitivity. The arm began meeting the demands of the offshore oil industry in 1976. Today, with enhanced performance and reliability, the arm continues to meet the challenges of difficult deep-sea applications. Originally developed by the Reentry and Environmental Systems Division of the General Electric Company, the arm now represents an improved capability for telerobotic work systems which will extend man's instinctive movements and sense of feel into even more remote environments. Normally mounted on a manned submersible or a remotely operated vehicle, the arm provides the dexterity of the human arm, allowing the use of underwater tools normally used by divers. The system consists of a remotely located master control and a task-performing slave manipulator located on the work vehicle. A single grip on the master controls all of the motions of the 7-function slave. This control system is unique in that it uses a spatially correspondent force feedback master-slave bilateral servo control system. The operator's master input motions are duplicated by the slave arm in a 1-to-1 angular displacement ratio and a 1-to-3 linear displacement ratio. Forces exerted by the slave or to the slave are sensed and fed back to the master to produce forces which provide the operator with a sense of feel in 6 axes of motion. The grip has programmable limits of force which are proportional to trigger squeeze. The nominal force feedback ratio is set at 13-to-1, such that slave forces of 65 pounds will be felt as 5 pounds by the operator. The arm's proven performance record is outstanding. Typical tasks are general rigging, object recovery and placement, non-destructive testing, ultrasonic and cathodic potential, operation of hydraulic quick disconnects, alignment of pins, control pod alignment and placement, operating valves, cutting, drilling, sawing, grinding, mate and demate of electrical connectors, operation of switches on dynamic positioning beacons, setting explosive charges, threading of nuts and bolts, use of impact wrenches. And this is just a partial list. These tasks have become routine for operators due to the human-like qualities inherent in the arm's exclusive bilateral servo control system. The arm earns the confidence of its operators by going far beyond simple duplication of human arm movement. Electronic force feedback and compliance make this internationally patented system unique. The features of the mechanical design and the biotechnology of the servo control provide a very instinctive bond between the operator, man, and the machine. The mechanical range of motion for each joint approximates the human range. With speeds at rated loads set as much as 120 degrees per second for the forearm and wrist motions, the operator can accelerate rapidly in order to make small and precise position alignments. Load forces, both static and dynamic, are sensed and transmitted to the master in direct proportion to the forces experienced by each motion of the arm. During the performance of a task, the operator exerts forces on the load with perfect control of those forces because he feels them. Electronic compliance adds even more to the dexterity of the system. By exerting a slight force on the master, the operator can gently trace the contour of a structure in conditions of poor or no visibility. Like a person blindly locating a bolt, the operator can sense the depression of the hole, then relax and allow the master to follow the arm, inserting the bolt into the hole. Sliding a nut over this bent rod is a good example of the coordination and dexterity that is possible with the arm. A rate control system would find this task nearly impossible, but spatial correspondence, force feedback, and compliance make this task a smooth precision maneuver. This compliant feature of the master following the arm also protects it from inadvertent damage. By relaxing his grip on the master, the operator allows the slave to comply and yield to the force. At the most critical part of the task, at the top of the rod, the operator relaxes his grip to allow the spring of the rod to center the nut and then slide it off without disturbing the springy rod. Turning this needle valve shows how the arm can maintain contact and spin the handle much the same as you might if it was done by hand. When the valve reaches the end of travel, then the grip is readjusted and up to 100 foot-pounds of torque can be applied. A standard quick disconnect can be demated and mated without special tools. First, the sleeve is retracted using a diagonal grip, and then with reliance on force feedback and compliance to maintain alignment, the fitting is removed. The process is reversed to install the fitting. This electrical connector was designed to be mated underwater by the U.S. Navy Civil Engineering Laboratory. This prototype is made of Delrin and could easily be crushed by the jaws of the arm. By reducing the programmable grip force, the operator handles this delicate task without risk to the connector, which must be precisely aligned. The use of this hand pump demonstrates a combination of tasks. As we mate this pneumatic fitting, the system maintains spatial correspondence throughout the operation with instinctive control. How sensitive is the arm? This scale demonstrates the sensitivity of the arm. At less than 3 pounds of force, the scale pushes the hand back. The operator will sense force levels of approximately 3.5 pounds. This level is primarily determined by the friction band of the wrist actuators. With 2 anthropomorphic telepresence manipulators, the performance of this bilateral control system, in conjunction with force feedback and dynamic compliance, becomes even more apparent. The assembly of this toy requires 2 hands. You are watching the first trial of the operator accomplishing this task. One hand, either the left or the right, is used as a jig or clamp to support the work. The opposite hand must then orient the part to be fitted and then complete the assembly step. With the assembly complete, the operator demonstrates picking it up without a physical grip. The assembly is held by maintaining mutual compression and point contact by the hands of the remote manipulators. Each arm must drive and each arm must comply as the object is translated into 6 axes of motion. The operator is in control of all forces and motion. You have seen this task performed in detail with the right arm. Here the work envelope is greatly expanded. With the right arm acquiring the nut from a remote source, handing it to the left hand, and with reasonable equivalent dexterity, the operator does the task left-handed. A realistic system requirement. Some tasks, such as the ball valve, can be done with the right hand or the left with equal skill since the valve is in reach of both arms. But 2 ordinary mechanical arms grasping a rotating handle at different points and 45 degrees to each other would have a difficult time with coordination. As you can see, this system does not. The task is a simple coordinated grasp and move. Using 2 hands makes the operation of a fluid or gas quick coupling a very natural event. The coupling is released and brought close to the camera and positioned for inspection. The part is transferred again and reconnected. And using force reflection, the operator can verify that the fitting is secure. A A series of tasks is accomplished here with a wooden block secured with an over-center clamp. Next, the operator acquires a nail from the remote component storage area. Here we use a permanent magnet to hold loose parts. The nail alignment is corrected. The operator acquires a hammer with his right hand and with considerable control is able to drive the nail. Oops, well, it didn't hurt much. Telepresence work systems with robotic modes of operation will find important application in space, and many tasks have already been identified. For the first space station, the following will require system servicing with telepresence intervention: radiator panel repair, logistics module installation, OMV propellant transfer, AXAF tank replacement, LDR assembly, comms platform and stage assembly, GRO subsystem module replacement. The service of free flyers has also been identified in the current studies for NASA. These tasks have been identified as drive mechanism replacement, battery replacement, replacement of instruments and manufactured products, and many tasks of opportunity which will be generated as needs arise. Telepresence work systems have many advantages in addition to keeping man in loop. Because man is interactively involved, these systems are insensitive to off-nominal conditions. They have moderate speed. They can perform complex operations. And tasks which require real-time decisions can depend upon the operator's sensibility. In addition, robotic control of the telepresence slave is easy to achieve with interactive software. Robotic control will enable performance of relatively simple and repetitive operations. The incorporation of telepresence teach mode will enable in situ programming and will greatly enhance the generation of ground-developed software by accumulation and analysis of empirical real-world situations. One of our first complex task demonstrations is a simulated assembly of a structural element with the installation of an antenna. All components are located within the large work envelope of the two remote slaves, and no maneuvering was required to accomplish this series of tasks. First, the structure is acquired, then brought into position. The structure is mounted on the peg pedestal. The antenna is acquired and transferred to the right hand. At this point, the operator is operating blind and must sense the hole. And, using force feedback and dynamic compliance, insert the mounting pin into the hole. The hex driver is acquired and installed on the impact wrench. The antenna locking screw is then secured. The assembly is repositioned and a different hex driver is required. The new tool is installed and the task is completed. Western space and marine people have been directly responsible for initial concept design, fabrication, and application of telepresence manipulator systems, which have accumulated in excess of 1 million operational hours in industrial, military, aerospace, and marine applications.